So, in Canvas, you got your home announcements, syllabus, and assignments. So when you're looking at assignments, the way that I organize Canvas, you want to show by type. If you show by date, it'll kind of be confusing. So always view this by type, because that's the way that I organize it. Okay, so you've already turned in homework day review. That was due at 9. You got 2 more things due Friday. This function notation worksheet, GC intro. Those both of those relate to what you'll do in recitation. But if you have a recitation tomorrow, I'd strongly suggest you just give it a try before. So you're not just giving yourself one night. So give it a try before, look at that, do as much as you can. And then in recitation, that will probably answer all your questions. Okay, remember you're getting GC, graphing calculator, loaded on your computer. If you can do that before recitation, so if you have trouble, then in recitation they can troubleshoot that, okay? So those 2 assignments right there, due Friday, 9 a.m. before class. Okay, and then in modules, I posted lecture videos. So this is the lecture video for, it's a YouTube video from class on Monday. And then you can always just come here and see the most recent video. If it's not up the evening of class, like the next morning, you feel free to send me an email and say, where's the video, okay? Because I want to get those up by the end of the day, at the very latest, usually in the afternoon, okay? So if you don't see it, it should be there. Don't hesitate to just send me a real short email. Okay, any questions about Canvas or logistics? All right, so let's start by going over the homework for today. Let's just talk a little bit about your homework. Setting the stage. So what are we doing? We are doing kind of a review crash course of one of the important problems in calculus, which is this one at the top. You know how fast a quantity is changing at every moment. You want to know how much of it you have. This could be argued this is like half of calculus. Half of calculus. You know how fast some quantity is changing every moment. You want to know how much of it you have at every moment. Okay, so this is relevant, right? This is we got quantities all around us, things that we measure all around us. And they're changing at a certain rate, all right? And so one part of calculus is about modeling how much is accumulating as that rate, if you have a certain rate of change of a quantity, how much is accumulating, right? And so that's exactly what this is asking, okay? So how fast a quantity is changing at every moment. What is that? Like how do we mathematically model that? What would you have that would be, you know how fast a quantity is changing every moment? For instance, the flag example. What is it that we had in the flag example that was, you know how fast something is changing, a quantity is changing at every moment? Yeah. Okay. And rate of change of what? What quantity? Okay, but so yeah, meters per second is the unit, but the rate of the negative 0.75 was the rate of change of what quantity? Yeah.
Height and time.
Okay, so both? Is it the
so meters is the height on times.
So is the rate of change is negative 0.75? Is that the rate of change of height and time? Just height, right? So the quantity in question here, so you know how fast a quantity is changing at every moment. Here we're talking about height above the ground. We know how fast that's changing at every moment. How fast is that changing at every moment? So that was our value of m. And how fast was the height changing at every moment? Go ahead. Negative 0.575 meters per second. That's telling us how fast the height is changing at every moment. Right? So here's the quantity in question is height. And here's how is the rate of change of height. All right, so we talked last time about the meaning of that rate of change. And maybe before yesterday's class, you might have said, oh, that just means that every second the height comes down 0.75 meters. Is that right? Every second? Flag descends 0.75 meters. Is that the meaning of that rate of change? Every second, the flag descends 0.75 meters. Is that the meaning of that? Some are saying yes, some are saying no. Is it a true statement? That's absolutely true. And that's a common way to express the meaning of that. But we talked about a broader meaning, a fuller meaning, a better meaning. And does anybody remember what that was? Yeah. So this only says that you know how fast it goes down in 1 second. Do you know how much it goes down in 1 second? Do you know how much it goes down in 2 seconds? How far does it go down in 2 seconds? Well said. Okay, well said. So do you know how much it goes down in 2 seconds? How much does it go down in 2 seconds? 1.5 meters. How much does it go down in 10 seconds? 7.5 meters, right? So you know a lot more than just how far it goes down in 1 second. You know how far it goes down in what variation of time? Any variation of time. What do we call any variation of time? We called that dx, because x was our number of seconds. So given any variation in time, 1 second, 5 seconds, 0.8 seconds, right, 10 seconds, we can know what the variation in height was, and we call that dy. So in this case, that's our variation in height for any variation in time. And how do we find that variation in height, she said? What are you doing to get, so in 10 seconds, it goes down 7.5 meters. So what are you doing? You're taking that 10 seconds and multiplying it by the constant rate. So this little equation here, it gives us this frames a much better meaning for what this constant rate means. I'm going to be asking you over and over again until it's not deer in the headlights, until we get it. A constant rate of change means for any change in the independent variable, you know how much the dependent variable changes. And that's by multiplying your constant rate times your variation in the independent. Okay, so whatever strength in your brain you can muster to start learning this right now if you haven't. Okay? So that it's not 3/4 of the way through the semester when it finally starts to click. Okay? Given any change in time, we can know how far the height has gone down. Not just 1 second. Okay, cool. So then where did this come from? This equation, a sub h of x equals negative 0.75 x minus 0.6. What's kind of the structure of that, or where did that come from? Anybody? I guess there were some hands in Monday's class that I was not seeing, so I'm looking today. I'm looking for hands, okay? Where does that equation come from? Okay?
Because the rate of change of the function stay constant.
Yep. Yep, he said the rate of change.
0.75
right?
per second, based on the graph.
Good, right. So the rate of change is constant. And what is the overall form of this?
Also, the function intercepted with the x-axis at 0.6 seconds.
Okay. And what did you say? Yeah, so this is the function notation for saying amount of variation in height. So this is dy. And then what was this? Okay, a particular dx, right? What particular dx is this? This is the variation of time starting from 0.6 seconds since the flag started being lowered. So this is a particular dx where we're after 0.6 seconds, it's like, okay, start the clock. That's our dx from there, right? So the change since 0.6 seconds. All right, so this function came from dy equals mdx. We got our function notation, super important. Well, you'll be reviewing that in recitation. And then this represents dx. Okay? So then we graph the rate of change and this function. And I ask you to interpret some points. So let's look at that. This is there we go. So they're the graphs, and then there's some black points on there. So did I add points to the graph? Did I add points to the graph? Yes or no? No, what did I do? So what's the why are these black points? Are these new points? Did I come along and put a new point on that graph? No, what did I do? It just like accentuated a point that was already there, right? I highlighted a point that was already there because what is this red line in essence? It's okay, it's a rate of change function, but the red line is the red line itself consists of what? A lot of points. That's how you have to train your mind to look at these graphs, whether it's line or a curve. What you're looking at is a zillion points, and every one of those points has a meaning. And so this point right here, first of all, what is the ordered pair? What is that ordered pair right there? It looks like 1 second and what's so that's that coordinate pair, and so that's a correspondence of our two quantities, seconds and rate of change. And so what is that point symbolizing? What does that point mean? Any volunteers? Yes, sir. That was awesome. Did you hear that? He said, at 1 second, the flag is descending at a rate of 0.75 meters per second. Okay, and then we got another point over here. Looks like 2.3. And what's the y-coordinate? Somebody else. What's the meaning of that point? What's the meaning of that point? Someone in the back. What's the meaning of that point? 2.3 comma negative 0.75. Yes, sir? Okay, is it just how fast it's going? Is that what that... Yeah, so exactly, at 2.3 seconds. So it means that when at 2.3 seconds, the rate of change is negative 0.75. And so we could do that a gazillion times here for every single point on there. But it just takes too long to graph graphs that way, right? It's like this would take too long, right? So what do we do? Just go, whoosh. But then in your brain, you have to look at that and think, oh, that's just all these points, correspondence of time and rate of change. Make sense? Okay, what about over here? So now this, we're understanding what these points mean is the way to understand what this function is doing. So what is this point right here? It looks like 0.8. And I think if you do the math, it should be negative 0.15. Is that right? Yeah. Is it right? 0.2. Yes. Okay. All right, now this one's a little trickier, but interpreting the meaning of this point correctly means you understand what this function is doing. So why don't you take 20 seconds to try to tell the person next to you, what is the meaning of this point right here? And you got to include all the details in your explanation. So find a person, about 20 seconds, 30 seconds, see if you can do it. Everyone's talking to somebody. What did you talk about? Okay, so what do you think the meaning of this point is, Sage?
We discussed that it's the change of rate at 20 seconds.
Okay, she said at 0.8 seconds, the change of height is negative 0.15. So there's one more detail that's important there. So yeah, everything's correct. At 0.8 seconds, the change in height is negative 0.15 meters. One more.
Would it be that at the rate of negative 0.75?
Okay, yeah, that's true. That's true.
We said starting at 0.6 seconds.
Yeah, so this change of height is over what change of time? The 0.2 second interval of time starting at 0.6 seconds. See that? So something like this. It doesn't have to be my words exactly, but the meaning of this point is that at 0.8 seconds, since the flag started being lowered, the flag has descended 0.15 meters since the 0.6 second mark. That's what we mean by net accumulation. Net accumulation is amount of variation since some point, right? Since some point. It doesn't have to be zero. So in this case, all these points will give the net change in height since the 0.6 second mark. All right, so I think we got it. So let's just practice one more time. So this is a 1.6 and negative 0.75. That's this point. Volunteer to explain that point. Somebody new? Anybody new? Want to tell the meaning of this point? Yeah?
Yeah, it's the total change in height from 0.6 seconds to 1.6 seconds.
Right. Which is, what is that?
That is going to be the dy, change in
Right. Excellent. Yeah, absolutely. Everything was right. So in your explanation, use those two numbers. So you can you do it again and then use those two numbers as you explain it?
Yeah.
Yeah.
At 1.6 seconds, the flag has descended -0.75 meters from 0.6.
Good. Right. Exactly. At 1.6 seconds, the flag's descended 0.75 meters since 0.6 seconds, or beginning at 0.6 seconds. Okay. Awesome. All right. Now you're going to be working on GC in recitation, and then, but I just want to do a little bit today, just so we can see as many little introductions as we can. So let's open up GC. Here we go. So when you open it up, it looks like this. The first thing about it is it's just a basic calculator. Regardless of graphing, you can put in expressions, and it will always update and tell you what the answer is. So suppose I want to know how much has, so there's my rate of change. How much would the flag descend in 1.82 seconds? Well, I can put in my m dx, negative 0.7, 1.82, and it immediately is telling me that the flag will descend negative 1.365 meters. And then you can come along and change it, and as you change it, what I meant was 3.82. As soon as you change it, it updates. You can copy and paste. You can use parentheses. So it's a really nice, just arithmetic calculator, okay? All right, so now we want to put that function in. So that function that told us the change in height since 0.6 seconds, so capital A, and then Control L if you want to get fancy and put a subscript in there. So Control L gives you a subscript. And then for function notation, I'm going to do Control 9 for parentheses, not Shift 9. This is really important because if you do Shift 9, what will it think you're doing? Multiplying, right? It's thinking, oh, this is some value, and you're going to multiply it by that value. Don't want that. So instead, you're going to do Control 9, and notice those parentheses are closer. They're further apart when it's multiplying. They're closer when it's actual function notation. And so I want my independent variable. What do we call our independent variable? We called it x, right? But we could call it anything. And then x and GC is a prompt. X is a prompt in GC to graph it on the x-axis. So I could make it anything. I could say I want it to be, say, capital T for time. All right? And then what was our function? What was the rule that gave us those net accumulations in height? 5 times, what should I put here? X? But I'm using T, right? I chose to use T, so T minus 0.6. Okay, and then I can come here and I can, so to do a new command line, you can do control return or command return. All right, so why didn't it graph it? Why didn't it graph it? Yeah.
Because you didn't put y equals.
Yeah, so a function itself is not the same as its graph. A graph is just one representation of a function. So what have I done here? I've just defined it. I've just defined this relationship between this value capital T and then values of the dependent variable, which is a sub h of t. So this is just defining the function. I could use it. So what was the one that we had? So what was that first point that we had? Was that 0.8? So if I do a sub h of 0.8, look, now it's using that function and telling me that the change in height since 0.6 was the negative 0.15. So the function, my point is a function is not synonymous with its graph. A graph is one aspect or one way to represent a function. By defining the function, it's just kind of telling GC about this relationship, and then we can use it in different ways. So here's one way I can use it. It's just find a value of the dependent variable when x is 0.8, or the input is 0.8. Now if I want to graph it, so to graph in GC, using x and y are what prompt GC to graph an x-axis horizontal and y-axis vertical. So where do I want to put values of the dependent variable? Do I want those to be on the horizontal axis or the vertical axis? Vertical, right? So I want to set those equal to what? Y, right? So I'm going to set values of the dependent variable equal to y. So y equals, and I want my independent variable to be what? Capital T? No, I want to tell GC to put values of the independent variable on the x-axis, right? So I used capital T as what's called a dummy variable to define it. But when I graph it, we need to tell GC that that independent variable T needs to go on the x-axis. So I'm going to do that. And then you can change the color by clicking on the box. These first three colors and black are the best. These are a little light sometimes. So I'll do blue. And when I graph it, there it is. Now, what part of that graph do we care about? Starting from where? 0.6. So what you can do is just type comma and then tell it. I only want you to show it for x, what? Greater than 0.6. So this says graph the function, put the dependent variable on the y-axis for the independent variable x, but then only show me for x values greater than 0.6. So that looks like what we had. And then we were interested in, so that first point was at what? 0.8. So to plot a single point, you use Control 2. Control 2 will plot a single point, and so say 0.8 and negative 0.15. I think it was. Was that point that we talked about? Yep. Okay. And so by doing Control 2, put your x coordinate top, y coordinate bottom. There it is. You got zoom functions down here on the left. Zoom in and out. Okay, but what if I wanted to plot the point for 0 or 1.369? How much change in height since 0.6 seconds occurred at 1.369 seconds? Well, there's something I can do here that's very convenient. So I could I could calculate that, do the arithmetic and calculate it. Or what could I do? Make this nice and easy, yeah. Right, so now I've defined this function, right? I want what? The value of this function when the independent variable is 1.369. So how do I represent that? A of, right? A of. This little thing that I'm doing right now is so hugely important. We're going to be doing it over and over again. This is called using function notation to represent values of the dependent variable. So in this case, the change in height since 0.6 seconds. So I'm going to do A of h of what? 1.369. So this is really helpful because this value is, it's the value of the function when the independent variable, in this case time since time is 1.369. And so then if I plot that, make it black, say, there it is. What if I want to know the value of that? So notice that this was perfectly legitimate without ever calculating the value. We just let GC do it and then show us that point. Okay, what if I want to know the value? What do I do? I can just enter that in a line on GC, and as soon as I put that in a line of GC, it tells me what its value is, based on the function I defined before. So this function notation is super powerful, really helpful for representing values of the dependent variable. And then by putting the function in, we don't have to we can let GC do all the work, right? So by putting the function in first, then we can just type in that, and we know its meaning, and then GC does the calculation and tells us what the value is. Okay, questions on this kind of very brief intro to GC, and you'll do more, like I said, in recitation, and then lots more in upcoming assignments. Okay, so the frustration with GC that students have is because of, for lack of a better term, sloppiness. Math is a precise language. If you're not precise with a mathematical language, GC won't know what you're talking about. It's not GC's fault. It's not GC's fault. It does exactly what you tell it to do. It doesn't read your mind and do what you want it to do. It does exactly what you tell it to do. So this is very good training for you. So we got to see this in a positive light. The frustration is it's going to catch you when you're not mathematically precise with the notation. It's got to be right. So I know it's frustrating, but try to remember, okay, this is training me to be a mathematician, which is precise language, precise symbolism and notation. Okay, any questions? All right, so we're on our journey here of, you know how fast the quantity is changing at every moment. You want to know how much of it you have at every moment. And principle 0 was variables vary. Principle 1 was constant rate of change. Principle 2 was a net accumulation function. We've talked about all those. So principle 3 is changing rate of change. Changing rate of change. So suppose, if a soldier is lowering a flag manually, is it going to come down at a perfectly constant rate? All right, so maybe this is a more realistic rate of change function for a soldier lowering a flag. So look at that rate of change function and tell the person next to you why might that be a more realistic rate of change function for the soldier lowering the flag. 20 to 30 seconds, go. Be specific, be specific. Matching what's going on in the graph.
Are those like notes on?
Don't worry about that yet. Okay. Yes, you're going to use that for notes, but I'll let you know. Okay, what do you think? So how can you match up what's happening in this graph to what's happening when the flag is being lowered? Somebody new? Anyone want to share what you thought? Yeah.
He says that like whenever it's horizontal at 0.7,
Okay.
that means that's when he's actually pulling it.
Okay, good.
Whenever it goes back up, that's when the rate of change is going to 0.
Okay.
So that it means that he's like taking a pause.
And why would you take a pause? Why would you need to take a pause?
Because you're probably not going to just keep going.
Okay. Where does the pause come in? Yeah.
Where he's switching hands.
Switching hands, right? Switching hands. So each one of these, that was really good. So when it's coming down, this is like one hand is pulling, but then you have to switch hands. What happens when you switch hands? The rope will kind of slow down and then pause for a moment, and then the other hand grabs on, and then again pulling down at the negative 0.75 meters per second. Okay. So this is a more realistic rate of change function. So what I want you to do on your worksheet on the page that does not have the table, that's the first page. So there's one side has a table on it. Flip it over from the table. And the first thing you're going to do is sketch, just a rough sketch. Don't do any calculations. Just think about it and make a rough sketch of what the new net accumulation function would be starting from 0.6 seconds still for this rate of change graph. So how would that change the net accumulation function? So you could discuss, think about it, make a sketch. Okay, so for time's sake, I want to get to stuff at the end. Is your graph something like that? So now it's the same idea. It's going to start at the 0.60. At 0.6 seconds, we have no change. There's no change since 0.6 seconds, right? And then it's going to head down. But then in these in-between hands, it's not going to decrease, right? So it's going to come to this kind of place where it just pauses, and you don't get an additional decrease in height. And then it decreases again to negative 0.75, and then a pause. Something like this. Something like this. Okay, in order to come up with this net accumulation function before, it was based on what? What did we use to get this net accumulation function? What was the key principle? That function was based on what? Constant rate of change. That a sub h was, essentially, it was mdx, right? What's the problem now? M is changing. We have a changing rate of change. All right? So this very simple equation, it doesn't apply when M is changing, right? Because that only makes sense if, or only works if M is constant. So this is this. So we come to a more realistic situation, and things suddenly get more complicated and harder. So this is how fast the quantity is changing every moment. That's our changing rate of change. And this is how much of it we have at every moment. Or it's closely related, right? Closely related to how much we have. It's a tracking amount of change, right? Tracking amount of change. So then the question is, how are we going to write the net accumulation function when the rate of change is changing? How are we going to do it when it's changing? Because it's like we can't use mdx because m is continually changing, especially in between hands, right? M is continually changing through there. So how do we come up with a net accumulation? Okay, so what we're going to do is we're still going to leverage this, right? So this is this powerful idea, this constant rate of change that changes our mdx. We still want to use that, but we've got to adjust. We've got to adjust. And so here's what we're going to do. I'm going to break up time intervals of 0.35 seconds, starting from 0.6. So starting from 0.6, I'm going to break up time into 0.35 second intervals. Okay? And in each of those 0.35 second intervals, I'm going to apply a constant rate of change, because then for the constant rate of change, I can use mdx and get the change in height. Does that make sense? So we look at this first interval. What constant rate of change should I use in this first interval to try to reproduce the rate of change function that I have? So this is pretty easy. What constant rate should I put in the first interval for 0.35 seconds? Should I put negative 0.5? 0? And what should I put? Yeah, notice that it's pretty much a constant rate of negative 0.75 in that first interval. So I can call that in the first interval. So this is what you want to do. So you're going to draw an, what we're going to do is we're going to create a new function on top of this that's going to have constant rates in each interval, because for constant rates we can use mdx. So in that first interval, the clear choice is to use negative 0.75. So yeah, now are we on this? Do we flip over to the other side now? Yeah, we're flipping over to the other side of the sheet. You can use this for your notes. You're on this. Okay? So now what about in the next interval? So the next interval, the rate starts at about what? It starts at about negative 0.75. Then it does what? It goes up to 0 and back down to negative 0.75, about, essentially, in that whole interval. So do I want to choose the constant rate of negative 0.75 again for this interval? So I want to choose, all I got one rate, a constant rate to try to represent what's happening in there. So what one constant rate would kind of represent all the rates in this interval. So everybody's answers might be different, but we should all be close to what? Something like the average of all those rates. So I chose negative 0.4. You might say negative 0.5. You might say negative 0.45. just eyeballing. So what am I doing? I'm picking a constant rate that's trying to be like the rate of change profile in that interval, or like kind of like the average of all the rates. Since it started at negative 0.75, went up to 0, and back down to negative 0.75, I just took something in the middle, like negative 0.4. Does that make sense? What about the next interval? Yeah, let's go back to, so most of that interval is at negative 0.075. So let's just call it that. Okay, now this next one, it goes from negative 0.75 pretty much to 0. So it covers all those rates. But then there's this part at the beginning where it's kind of all negative 0.75. So what would that do kind of to the average? It was going to pull it down a little bit, right? So there's more of the interval that's lower. So I chose negative 0.5 for this interval as trying to mimic or simulate all those rates, like an average of all those rates, and call it one constant rate of negative 0.5. Does that make sense? Next interval. So now this one, it starts at 0, it goes down to negative 0.75, and then it has a even bigger chunk of it at the bottom. So how would this one compare to this one? Even a little bit lower, right? Have a bigger chunk of the interval. So I called it negative 0.6. Again, if you were doing this, you might get slightly different numbers, but these are all would be in the ballpark. Notice this next interval is kind of the mirror image of the last one. So I chose negative 0.6 again. And then the next interval is the mirror image of this interval. Back 3 now. Do you see that? This interval is like the mirror image of this interval, so I chose negative 0.5 again. And the last interval, negative 0.75 again. So I'm trying to leverage MDX. What that means I need constant rate. So I'm going to break up into intervals, and then in each interval, pick a constant rate that's like kind of the best at reproducing the changing rate in that interval. So it's kind of like the average of all the rates in that interval by eyeballing. Okay, so this is principle 4. This is creating a pretend rate function. A pretend rate function. So I'm creating a new function that's pretending to be the changing rate function, but is made up of constant rates so that I can use MDX. Okay, gotta move. All right, so then you see this table here. So before we start filling out the table, we want to understand the table. So I have 3 questions. Make sure you answer and understand these questions before you start punching the numbers. And when you get into punching the numbers, don't lose sight of what the meanings of things are, right? So first of all, why are the columns staggered and offset in the way that I've done that? There's a reason. It makes sense to do it this way. Okay, why are these 2 middle columns staggered and offset, and then this last column is back to like the first one? What key concept allows for computing approximate rate of change? Okay, the second column, the first one you fill in, those are the rates that we picked for each interval. Why is the column staggered? Why is it offset? Yeah.
To represent the interval of 0.35 interval.
Right, because this rate of change, this constant rate of change, it applies from the interval starting from 0.6 and ending at 0.95. Does that make sense? And then this negative 0.4 that we chose, it's the constant rate for the whole interval starting at 0.95, ending at 1.3. So it should make sense that I'm staggering the columns like that. Okay, so then at that rate of negative 0.75, how do I get the corresponding approximate rate of change? How do I get that? I want to know. So it's descending at a rate of negative 0.75. What amount of change in height do I get for that? How do I calculate that? Yeah.
Is it the rate of change
Over? So approximate change in height, those are dy's, and we get dy by mdx. Should use a different color. All right. So mdx, what's my m? My constant rate in that interval. What's my dx?
Negative 0.26.
No, my dx. It's my dx.
Closer to 25.
The amount of change of x is 0.35 times the rate gives me 0.625.
0.2.
26.5.
Thank you. And then we're going to get another little amount of change in the next interval, but at this different rate, right? So now I've got the rate of negative 0.4. So what I'm going to multiply the negative 0.4 by? The variation in time is, again, 0.35. So 0.35 times negative 0.4 is? 14?
Yeah.
Is that right? One more. Next interval, back to negative 0.75 as the rate for another 0.35 seconds, mdx. Is that right?
One.
Is that right?
Yes.
Yeah. Okay, so now, what is this column? This column is approximate net accumulation of height at x seconds. So the net accumulation, again, since 0.6 seconds. So how much accumulated change in height do I have? What? At 0.95 seconds. So we're back to the unstaggered column because these are going to be amounts of change at these particular moments in time. 0.95, 1.3, etc. So how much accumulated change in height do I have at 0.95? Yeah, so I started at 0 amount of change, and I've just changed the height by this much. Does it make sense? Then 0.35 seconds later, I'm asking how much net accumulated change do I have? What will I do? I'm going to take how much change I had before and include the new change. So I'm going to take that, I'm going to add on the negative 0.14. What do I get?
Negative 0.425.
That's right. 4425?
4.2.
Just 425? 4025. So it's right? What I have is right? And then at 1.65, I have all this change in the height from before, and then I got a new amount of change in this next interval. So my accumulated change. Accumulation means you keep, it's a running total. Accumulation, you're like, it's a running total of changes in height. Yeah.
Why is the change in height from negative 0.1? I got 0.17.
Is it 0.175? Okay, sorry, because I just was not thinking. Thank you for telling me that. All right, so now the next one is, I've got all this accumulated height at 1.3. I've got another interval of 0.35 seconds where I got this much more change in height. So now my new at 1.65, my new accumulated amount is 665. Where in this table is the net accumulation function? Net accumulation means you've got independent variable and dependent variable. So in which column is my independent variable of that function? 1, 2, 3, or 4? 1, x. And where's the dependent variable of the net accumulation function? 2, 3, or 4? 4. So what is this? This table is creating the net accumulation function based on constant rates in intervals of 0.35 seconds. Given any time, it tells you what? How much the height has changed since 0.6 seconds. Or this thing. Right? Okay.